Welcome to another video of our course in probability theory. We learned about almost true convergence, convergence in probability, and today we are going to have yet another kind of convergence, which is weak convergence. This is the kind of convergence that you have in the central limit theorem, which you might know from the theorem of Dumois and Laplace. And it has some theory behind it. So let's get directly started. So, weak convergence. Let me start by saying some notation we need. Weak convergence that we have today, there we will have multiple probability measures, usually. And for this reason, because we also have to integrate against them, we will use the notation probability measure, square brackets, x is the integral of x dp. So that's the expectation with respect to p. So we do not write e for expectation, but we write p for expectation. Because we will have many probability measures. Then we need a notion for the set of all probability measures on the Borel space on E. So E is a nice space, a polished space or so. We also need yet another kind of convergence, not only weak convergence, but so-called vague convergence. And for this, we need the sub-probability measures, so probability measures which integrate to something less or equal to 1. And weak convergence is tied very closely to this space of function, and vague convergence is tied to this space of functions. So for weak convergence, we will need the continuous bounded functions e to r. And for vague convergence, the continuous functions with compact support. So just to remind you what compact support means, that means there is a compact set, let's call it k or so, such that the function is 0 outside. So these are all real-valued functions. So this is a function f in C of E. And of course, it's continuous. It is also bounded because when it's continuous and it has compact support, it is also bounded because on a compact set, all continuous functions are bounded. So that's the subset of CB of E. Okay. Let's define weak and vague convergence. And the main point is here for weak or vague convergence, what actually converges is integrals. So expectations with respect to p and converge to expectations with respect to p. For weak convergence, that must hold for all f continuous and bounded. And for vague convergence, it has to be all continuous functions with compact support. And as we just said, so this inclusion here holds. That means vague convergence is less restrictive, or every weak convergence sequence is also vaguely convergent, but not the other way around, as we will see. I will probably very often say just weak convergence, but you might also say if you have random variables, they converge in distribution, so not in probability, that's something else, but in distribution. If and only if, well, their image measures converge weakly. Well, you can also say this a bit differently because, well, integrating some function f with respect to the image measure, we had this transformation formula that's the same as p, well, xn converges as n goes to infinity to p f of x for all f in CB of E. And just to be very precise, I didn't mention here these random variables, are they defined on the same probability space or not? And actually this here even holds, or you can even formulate this, if they are defined on different probability spaces with different probability measures, as like this here, so Pn f of xn, and that's also how that's here. So xn is defined on the probability space where you have the probability measure Pn. Very often you have the same probability space, then the P doesn't have an n. Okay, some first examples. Let's have a sequence of points in R, and let's take the Dirac measures on these points. Then we have that the Dirac measures converge weakly. Okay, why do they converge weakly? Well, integrating with respect to f, so that's something you have to keep in mind. So what is this? Pn f, that's the integral f of x delta xn dx. Well, and this here is 1 if and only if x equals xn. So this here is f of xn. Like here, that f of xn converges to f of x because f is continuous and xn converges to x. And this in turn is p of f. So integral of f with respect to p, which is delta x. So that's the first example of weak convergence. And for weak convergence, we have the following example. So we have some xn which goes off to infinity. Then the corresponding Dirac measures converge weakly to the zero measure. So the measure which is zero all the time. Why is that? Again, Pn of s, so the integral equals f of xn. F of xn, okay, that's f of n, but f has compact support. And since f has compact support, f of n will be zero eventually. And when it's zero, it doesn't, well, get better, so it stays zero, so it converges to zero. And zero equals the zero measure integrated with respect to f. So keep in mind, this zero here is a real number, and this zero here is a measure, the zero measure. So the point is really here, since you have compact support, you might, f of xn might run out of it, and you get zero, and that cannot happen here, because here the functions are bounded and do not need compact support necessarily. Okay, next example. If you have identically distributed random variables, then they converge. Okay, it's easy to see this because the integrals of f of xn are the same always, because xn and x, okay, they all have the same distribution. And that means weak convergence really is a statement only about the distributions of the random variables. But that might have been clear already from the formulation. But it's always good to keep this in mind, that you're never talking really about the random variables themselves, but on their distribution when you talk about weak convergence. And as you will see, the theorem of de Moivre-Laplace, you could formulate like this. Xn b and p and xn minus np divided by square root of the variance converges weakly to x, which is n0, 1 distributed. And we will see that that's something, a reformulation of the theorem of De Moivre-Laplace from your basic probability course. Okay, we have a new limit. And always when you have a limit, it would really be nice if the limit is unique. So if Pn converges weakly to P and also to Q, then P must be Q. This also holds here, but it's not completely obvious. But it goes like this. You have to show that P of A equals Q of A for all A closed. That's enough, because two measures are the same if they are the same on a pi system, so on a intersection stable generating system of the sigma algebra. The closed sets are such a system. So once you have shown this, you are done. We have a metric space, so we can define the following. The distance of a point x to a set A, that's the smallest distance of x to any point in A, so that's this distance here. And we have a closed set at the moment, and we need to approximate somehow this closed set, and we do it like this. Well, let me draw an example. So here's your closed set. Here's one. And I do it like this. And the slope of this line is m, which is this m here. So when you are here 1 over m far away from your set A, then you hit 0 and you take the positive part, so you do not become negative. But you have this picture here. So if x is in A, there's a 0 here, so you have 1. If you're further than 1 over m apart, you get 0, and then you have a linear decrease of the function, so that's like this here. And the point is, this here is a continuous and bounded function. On the one hand. On the other hand, fm goes to f pointwise. For this statement, I need that A is closed, because if it would be open, that would not hold at the borders here. But since it's closed, that works pointwise. And I have to show P of A equals Q of A. On the one hand, of course, pi of fm. Wait. These are the wrong brackets. P square brackets fm, because it's an integral. This here holds by dominated convergence, because fm, doesn't converge to f, but the indicator of A, I want to say. Here. So this here is dominated convergence. Pi of fm, so this integral here I can approximate by pi n of fm, because pn converges to p weakly. So you have this limit and to infinity, limit n goes to infinity, pi n fm. But since we also have the pn converges weakly to q, this limit here is also q fm, and since fm converges pointwise to the indicator function of 1, you have this bounded convergence. You have that this here is q of A, and we have shown uniqueness of the limit. Of course, since we have a new notion of convergence, we need to see how that interacts with our other forms of convergence. Now we have this result. Let me see if I can find this graphics I looked for. So here we also have V convergence, and we have from convergence probability we also have V convergence, and if the limit is constant we can also come back here. That's exactly this statement. So polynomials, they converge in probability, then they also converge weakly. And let me see if I can show this. It's by contradiction. So I suppose that xn goes in probability to x. And I also assume pi of f of xn does not converge to pi f of x for some bounded continuous function. That's what I want to have by contradiction. So I say, well, this holds, but this does not hold. And then I must get a contradiction. So this does not hold. So what does this mean? I can choose an epsilon bigger than 0 and a sequence n1, n2, and so on. So a subsequence such that p f of x and k minus p f x absolute value converges k to infinity to something bigger than epsilon. Yeah, because there's no convergence here, I can take a subsequence where it is above some epsilon bigger than 0. Since xn converges to x in probability, we already know by the general graphic here that we can find a subsequence with almost true convergence. I'll take this, take nk1, nk2, and so on, such that xn kl converges as L goes to infinity to X almost surely. But that cannot be because if, and since it's a subsequence, it converges here the same way as here. Because the sequence converges, any subsequence always converges to the same point. But xnki converges to x almost surely, and we know then by dominated convergence that the integrals also converge. So I have a contradiction with the fact that this here should be bigger than epsilon. And I'm done. So contradiction. So we have proved the first direction. For the other direction, so I want to show if x is constant and xn converges weakly to x, then it also converges in probability. And for this, actually, I need a fact. Where did we have this? Here it is. So remember, xn converges in probability to x if and only if this expectation here converges to 0. So distance of xn to x bounded from above by some constant that converges here to 0. So I can use this. Well, in fact, here I have to show this because I have V convergence, x is constant, and I have to show xn converges in probability to x. what I can do, integrate Rxn comma c, where x equals c now. And x is a constant, so x equals c, minimum 1. So what does this here do? And when I show that this here converges to 0, I've shown, according to this formulation, that I have convergence in probability. But I can show this because the function which maps x to the distance of x to z, minimum 1, is a bounded and continuous function. And we know for bounded continuous functions, because we have B convergence, that the integrals converge here. Pi of, well, c, comma c minimum 1, which is 0. So it follows that xn converges in probability to x. Okay. Let's come to one very large result. This is the so-called portmanteau theorem. There are equivalent formulations for weak convergence. So first, as you know, okay, xn goes to x. That means that integrals converge for all bounded and continuous functions, but it's equivalent, as it states here, if I restrict myself to bounded and continuous Lipschitz functions. There are 3 more things which are the same. If I have an open set G, that then this here holds, so pi of xn in G is bigger or equal to pi of x in G. It's also the same if I have closed sets, pi of xn in F smaller or equal to pi of x in F. And it's also the same if I have a set with, well, so what's this funny thing here? I hope you know this. So border of B is closed minus open. Yeah. So for example, border of an interval a to b is points a and b. And does not matter if I have closed here or open intervals, the border is always this here. So it's also the same that being in a set converges for all sets where the border has measure 0. Yeah, like this here. Then let's try to prove this. So first of all, what's clear anyway? 1 implies 2 is clear anyway, because for 1 I have to check this equation here for all boundedness functions, and for 2 I only have to check it for Lipschitz functions, so that's easier. And 3 and 4 are equivalent. That's also clear, because if I have an open set, I have that the complement is closed and vice versa. And if I go from G to the complement of G, well, I get a 1 minus. And with the minus sign, the lim inf becomes lim sup. And the bigger or equal changes to a lesser equal. So that's clear also. But let's try to prove the interesting parts. 2 implies 4, for example. I need F is closed. Epsilon k is a sequence which goes to 0. And now there's a trick that we already know, which is taking this function which uses the distance to the set f, so fk of x equals 1 minus 1 over epsilon k, distance of x to f, plus, like this here. So why is this good to check? Because the fk, so they are Lipschitz functions, with the Lipschitz functions 1 over epsilon k. So by 2 I know something converges. On the other hand, I know, since I have the closed sets here, that this function here converges to the indicator function of the set f. And I can write, well, lim sup n goes to infinity, so that's what I have to see here. The 0 must hold. Pi of xn is in f. Okay, that's I'm integrating the indicator of f. That's less or equal than the integral of fk of xn. Yeah, lim sup over all n. This here equals, since I have 2, to pi integrate fk of x. So here I need 2 because the integrals here converge. And well, that holds for all k. And well, this here, if k goes to infinity by monotone convergence, goes to p of x in f. Because the fk is converged to the indicator of f. And I've shown my first bit of the Portman-Tool theorem. Then let's take the next bit. 3 implies 1. 3 implies 1. So here I have the convergence of some open sets, and 1 is the convergence. And I'm doing this in some steps. So I take a bounded continuous function, which is non-negative, well, and bounded by some c. That's actually enough because, well, these integrals, I can always say, well, I take the positive part of f and the negative part of f, and if they converge separately, then I can also combine the convergences. So taking such an f is general enough. So let's see, p f of x. That must be the limit of the integrals of f of xn. And since f of x is non-negative now, I can do the following trick. Pi f of x bigger than t dt. We have that if you have a non-negative random rule, I can compute the expectation by computing this integral over these things here. And that's a clever trick in this sense because, well, f is continuous. The open set from t to infinity is an open set. And that means the set where f of x is bigger than t is also an open set because continuous functions maps the pre-image of open functions is open under continuous functions. So this here holds on, that's an open set. And since I can assume that I know 3, I know something about open sets. So this here is less or equal integral 0 to infinity lim inf pi of f of xn bigger than t dt. And I have the lemma of Fatou, which tells me I can take the integral after the lim inf and only make it bigger. n goes to infinity, pi f of xn bigger than t dt. And this here is, as before, the integral of pi with respect to f of xn. N goes to infinity. And I'm not done yet, because I've only shown that the lim inf here is bigger or equal to this here. But for the lim sup, I can make a trick and use my result I just proved. Lim sup n goes to infinity, pi f of xn. I can write f, so f equals c minus minus f plus c, like this. Yeah, that's what I want to do. Because minus f plus c, so minus f is between 0 and z. So this here is again a non-negative bounded continuous function bounded by c, and the c minus I can pull out of all the integrals. So I have that is c minus lim inf, so the lim sup becomes lim inf if I pull the minus sign out. N goes to infinity, pi minus f of xn plus c. And we have shown that the lim inf is bigger or equal to something, but minus lim inf is then less or equal than something. I combine everything, p f of x, so this integral here. So I've now shown that the lim sup is smaller or equal to p. P is smaller or equal than the lim inf, and of course the lim inf is smaller or equal than the lim sup. And I'm done with this. Then we're not done yet with the Portman-Tull theorem. It's a quite big theorem, but we are on a good way. Next, I want to prove that 3 and 4 imply 5. So we said already that 3 and 4 are equivalent. So I have some set B, and I can analyze the probability that X is in the open, the inner of B. That's an open set, so I can use my result 3. It's more equal to lim inf n goes to infinity, pi xn in the inner of B. This here is obviously, lim inf. I bounded from above by the lim sup. N goes to infinity. And I only make it bigger if I say xn is in the closure of B. And I'm doing this because then I can use this here, smaller or equal than pi of xn in B, in the closure of B. But no n here, of course. And this here because we have that the boundary of B has measure 0. There's, I cannot write it like this here, I have to write pi of x in boundary equals 0. Then it makes sense. But the probability that x is in the boundary of B is 0. That means the difference between these two here is 0. So this here is again this, and all equal or less signs become equal signs. And I'm done because that's what I wanted to prove. On the other hand, 5 implies 4. I take a closed set. And that's another trick here. F epsilon is the set of all x's, which are x, f smaller or equal than epsilon. So if I have a set f here, f, I make it a bit larger by epsilon. So this here is f epsilon. And why is that a trick? Because I know that pi of x in this border of f epsilon must be 0 for almost all epsilon. Because the boundary of f epsilon, if epsilon is different, this boundary is also different. So, and there are uncountably many of these sets. But yeah, so they cannot all have a positive measure, because then you would have a probability measure which sums to something much too big. So I have this here, and I can then use this and say lim sup n goes to infinity pi xn in f. That's of course smaller or equal than lim sup over n goes to infinity. Pi xn is in f epsilon k. And the epsilon k is now a sequence such that the bounds always have probability 0. Which means since 5 holds, this here is pi x in f epsilon k. And since f is closed, this here drops to pi x in f. And now I'm done, I hope, yes, because I wanted to show 4. And here I have the correct equal or less sign, and I'm done. Very nice. So, what else? Convergence in distribution we had, and maybe I write it like here. Yeah, that's my motivation for the next result. So usually what you show in your basic probability course is the following. Theorem of the Moivre Laplace, xn is binomial distributed with n and p, and you show convergence of the distribution functions, like this here. That's what you show, and I claim that's the same as V convergence, but we need to find a connection between convergence of the distribution functions and V convergence. And that's this theorem here. So I have probability distributions with the distribution functions f1, f2, and so on. Then V convergence implies if and only if you have pointwise convergence for all continuity points of f. So here I have the limit distribution function, and then on all continuity points I have something here. Of course here that doesn't play a role, because the distribution function of the standard novel is continuous everywhere, so the continuity points are all points. Okay, so there are two things to it, from left to right and from right to left. From left to right, x is a continuity point. Then I have the following, the p of the border of minus infinity to x. That's p of x. That's 0. Yeah, so Yeah, so continuity point is exactly a point. Continuity point of f is a point where this is 0 and fn of x, so I have to show convergence at all continuity points. Fn of x is p n minus infinity to x. This here, since I have V convergence, I can use part number 5 here, V convergence of the probabilities, pi of minus infinity x, which is f of x. And I've done with one direction, and for the other direction I will not do that here, but say please read it in the manuscript, because it's a bit harder. I already, I hope, convinced you that the old theorem of de Moivre-Laplace is weak convergence, so that's what we now have, because these are just the same. And the continuity points are all points. And I'll end this video with 3 results. One of them I will prove, and the other 2 of them I will not prove here, but they're proved in the manuscript. One is so-called Slutsky's theorem, which goes as follows. If xn converges weakly to x, and xn and yn are close in the sense that their distance converges in probability to 0, then also yn converges to x. Wrong arrow here, like this. Yn also converges weakly to x. Yeah, that's sometimes useful if you can only show xn converges weakly to x. You can show xn and yn, they're close, but you really want to have yn converges weakly to x. Okay, let's take a Lipschitz function, which is bounded and continuous. We do that because we learned in the Portmanteau theorem that's enough to show convergence of integrals with respect to these functions here. And we also know f of x minus f of y. Since it's a Lipschitz function, there is a constant L such that that's less or equal than L times the distance. But we also know that since f is bounded, that's bounded from above by 2 times the maximum of f. So we have this bound here for all x and y in E. And we can use that for some dominated convergence. Lim sub n goes to infinity. Well, p f of xn minus f of yn, like this here. I can bound this from above by saying, well, taking the absolute value inside here, and inside, well, I have this p L times r of xn and yn minimum to absolute value f, like this here. Yeah, and this here, well, this here converges to 0 by convergence in probability, since, well, that's very similar to here. We have convergence probability if and only if this here holds. Okay, we have now something here and not a constant 1 here, but something else, but that's still true that this here is equivalent. You can go through the proof if you like. So we have this here converges to 0. And, well, now it's an easy exercise of limits. Lim sub n goes to infinity. So what should we need? We need the integral of f of yn converges to the integral of f of x but we can say, well, soup, I take the integral of f of xn in between, so I have pi f of yn minus f of xn plus pi f of xn minus pi f of x, like this. And this here goes to 0 because the first term goes to 0 as we just showed. The second one goes to 0 because xn converges weakly to x. And we're done with Slutsky's theorem. There are two more results. The first is called the continuous mapping theorem. And first of all, the following simple thing holds. If xn goes weakly to x and phi is continuous, then phi of xn also converges weakly to phi of x. Why is that? If I take a function which is bounded and continuous on E prime, so the image set here of phi, then I can make G composed with phi. This here is a bounded and continuous function. It's bounded because G is bounded, so no value can exceed some constant. And it's continuous because compositions of continuous functions are continuous. And that means that the integral of G of phi of xn converges as n goes to infinity to the integral G of phi of x. And that means if you look at the phi of xn here, that phi of xn converges weakly to phi of x by definition. Okay, so for phi continuous, we have this. And the continuous mapping theorem actually deals with non-continuous functions, which is a bit strange. But nevertheless, I have here phi is a measurable function. It doesn't have to be continuous. But the catch is that the continuity points, so the points where phi is not continuous, have measure 0 for the limit. So similar as in the portmanteau theorem, that we have something with, the boundary of the continuity set of the boundary of the set of continuity points of phi. So it's this here, but it has measure 0. And then if you have xn converges weakly to x, then also the function of xn converges weakly to the function phi of x. Okay, that was the first. And the second is, I call that an abstract nonsense result. It connects weak convergence back to almost sure convergence as follows. I have renderals and they converge weakly, and that holds if and only if there is a probability space and renderals y, y1, y2 and so on, such that yn converges almost surely to y and the y's are exactly distributed as the x's. Yeah. Stupid example would be x, x1, x2 on, and so on. They are IID. As we know, xn converges weakly to x because their distributions are just the same. And then we can define y equals y1 equals y2 and so on equals x. So these are definitions of all these things here. Then I know, because the x's are all IID, so y, y1, y2, and so on, they have the same distribution. Okay, I need like this. I have, since everything has the same distribution, y is distributed as x, y1 is distributed as x1, and so on. But of course, since they're all the same, they also converge almost surely to y. Almost surely, because they're the same anyway. Okay, that's a stupid example maybe, and that result very often is not useful, but I wanted to mention it because it reconnects the convergence to some very strong form of convergence, which is almost true convergence. The downside of the theorem is that you have no idea what this probability space here will look like. Okay, that was the introduction to V convergence, and next time we will continue with our study on V convergence. See you then.